Today it is an honor, pleasure. I don't know what other adjectives. Or no, not that one. It's a pleasure to have Hugh Morrison visiting us here at LEAP. Hugh is visiting is a let's see, I should have written something down. Hugh is a senior scientist at National Center for Atmospheric Research in Boulder, Colorado. Hugh received his PhD in time immemorial at from University of Colorado as well. And I don't know any history about him besides that. So that'll have to do. He's going to talk to us a little bit about microphysics and new methods and a little bit of where machine learning fits in as well.
Okay, thank you, Marcus. You covered all the important things. So I'm going to talk about how we can improve cloud microphysics and Earth system models. And I use the word toward here because you're not actually going to see any Earth system model simulations. It's about kind of taking the steps needed to get to there. I do want to thank a number of people here, in particular Marcus, Kate, and Arthur, who I think is somewhere in here. Yeah, right there. As well as several others here who contributed to this work. Okay, as an outline, I'm going to discuss some introduction and background of, very simple things like what is microphysics, so we're all on the same page. And then I'm going to talk about some of the basic methods of parameterizing microphysics. There's three main ones. I'll go into detail on more, bulk bin and Lagrangian. And then specifically about improving warm microphysics or liquid microphysics in Earth system models. Okay, so as some background introduction, first of all, kind of a very basic slide. What is microphysics? So this is the collection of microscale physical processes involved in the formation and evolution of cloud and precipitation particles in the atmosphere. And the main point of this slide is that it's very complicated. There's a number of different specific processes that operate on these particles, things like condensation, evaporation, melting, and so forth. And you have many different particle types, as we all know. So you have liquid drops that form on aerosols when they activate. Those drops can grow by condensation and then later by collision-coalescence. Those can freeze and form ice particles. Those ice particles can consequently collect liquid water, which freezes, and they can rime. They can also grow by vapor deposition, and they can stick together and aggregate, fall out, and subsequently melt into raindrops. So it's a complicated picture, and the main thing that microphysics schemes have to do is to try and boil down all this complexity into something that's tractable and simple enough to actually use in a model. So there are two critical and distinct challenges to this problem. The first is an inability to represent every individual cloud and precipitation particle, even with massive advances in computing. And this can be illustrated by thinking of just a relatively small cloud, say 1 kilometer cubed, for a typical droplet concentration that can easily have 10 to the power of 17 drops. So we're not going to be modeling that anytime soon. The main question then boils down to essentially how can we represent the particle population statistically and relate it back to the model parameters or variables that are actually kept track in the model, they're resolved. The second main challenge, distinct from this, is the fundamental uncertainty of many physical processes at the scale of individual particles, especially for the ice phase. These are things like how ice particles grow by vapor diffusion. It's actually a quite complicated problem. We all know that there's different particle shapes and habits, but also how particles collide and stick together and grow. There's also some fundamental uncertainties even for liquid microphysics. Things like drop breakup are still quite uncertain. So the main point is, even if we could explicitly model every cloud particle, which I'm arguing in point one here, we can't, there would still be critical process level uncertainty. Okay. The other important thing is that when we have models in clouds, of course, the dynamical part of that model is not resolving all the relevant scales of motion. And this kind of illustrates that. I'll walk through this a little bit. So we do have the scale of individual hydrometeors on the left here. So this goes from left to right scales of relative motion here. So the scale of individual hydrometeors on the order of microns to maybe millimeters. Those can be modeled with every particle and modeling all the scales of turbulence with direct numerical simulation or DNS. And I'm going to give some examples of this later. But because of the small scales involved, these are limited to small domains, less than 1 meter cubed currently. So in models of larger scales than that, we can't model all the scales of turbulence. So these have to use a subgrid scale turbulence closure, and we can't model every particle, like I just argued before in the last slide. So these have parameterized microphysics. We're statistically representing the drop size distribution inside clouds that are mostly resolved. So we have to apply turbulence closures, but we're at least modeling part of the turbulence. That's where the large eddy comes in. We're modeling the largest eddies of turbulence, and then we can apply these turbulence-based scalings for the closure to kind of close that problem. And these are sort of well-posed, modeling most of the scales that are important in driving the cloud dynamics. As we get to larger scales than that, say kilometer scale models, convection permitting, or more often now called convection allowing models, and in the past have been called cloud resolving models, the scales of motion are no longer, the large eddies are no longer explicitly resolved. So you have under-resolved clouds, even though they can represent some aspects of convection, it's under-resolved. And they, of course, still have parameterized microphysics in that. As we go to even larger scale models, say mesoscale models in the order of 10 kilometers or tens of kilometers, to traditional global models in the order of 100-kilometer scale, less and less of the scales of cloud motion are parameterized. And they rely more and more on having to parameterize the clouds and the cloud motions. So we've referred to this as basically you have parameterized microphysics inside parameterized clouds, so parameterization squared, which presents a lot of, I would say, critical challenges in representing these clouds in global models and our system models. I'm not going to talk about that part of the problem. That's often referred to as the macrophysics part, as opposed to microphysics. I know those two words can sound similar, but the macrophysics basically refers to the subgrid scale variability of cloud water and the cloud fraction and the subgrid scale motions that are driving those. So I'm mainly going to talk about the microphysics part of the problem, and primarily from the standpoint of scales relevant to large eddy simulations. Like I said, I'll talk a few slides about some DNS that we have, some DNS results. All right, so that sets the kind of broader picture. So let's dig a bit more into some of the basics of microphysics parameterizations in current models. And they can be broken down into three main types. Bulk schemes, in which just one or a few quantities are predicted explicitly, things like the cloud mass mixing ratio. And these are computationally cheap because they have relatively few variables and relatively simple. Bin schemes, in which that particle population is discretized into size, or more commonly mass bins, and then one or two quantities are predicted in each bin. So these don't have to assume anything about the underlying size distribution. They evolve that explicitly, but they're much more computationally expensive. They usually have an order of magnitude or more number of predicted variables than bulk schemes. And the third is quite a bit different than the first two, which are Eulerian-based. There are Lagrangian particle-based schemes that are really, I would say, coming to the fore now in the last 5 years or so, in which the particle population is represented by a collection of so-called superparticles that move in the flow. So these are computational particles that move around in the flow, and each of those represent some multitude of real cloud and precipitation particles. And by the way, if anyone has any questions or anything, since this is kind of digging into some details, just let me know and we can address that, especially for clarification type questions. So I'll talk a little bit more about bulk schemes. This really comes out of a man named Edwin Kessler. Many of you have probably heard that name before. And he essentially developed and set the stage for the whole framework of bulk schemes. And I like this quote from a retrospective paper that he wrote in '95, talking about his scheme development in the 50s and 60s. And I'll read it now. He said, "I worked with a strong sense for interactions among processes and an expectation that their study would be facilitated by simple means to portray microphysical processes." So what does that mean? It's basically means that he's not trying to model the clouds and precipitation explicitly. He's trying to parameterize their effects in basically the simplest way that can reasonably capture those effects. So he came up with this idea of separating liquid water, and this is a liquid-only microphysics scheme I'll mention, but he separated the liquid water into two categories: cloud, which represents small drops, and rain, which represents large drops that can fall here. It's indicated by this sedimentation. So conversion is required when cloud droplets grow into rain, and that's modeled with two processes: autoconversion, which represents the collisions of individual cloud droplets together to form embryo raindrops, And then accretion is the growth of existing raindrops by collisions of cloud droplets. And I'm going to talk a lot more about autoconversion in particular in some later slides. And then, of course, you have to have conversions between water vapor and the liquid water categories through condensation and evaporation. So it's quite a simple scheme. So that was in the late 60s, but bulk schemes remain the workhorses of weather and climate models now because they're simple and cheap, like I mentioned. But since Kessler's work, now I'd say this is approaching almost 50 plus years, there have been many developments. Two particular ones are the inclusion of ice microphysics. We know the ice particles are obviously important in the atmosphere, and they have many important different properties compared with liquid particles, like, for example, their optical properties and how they form precipitation. And then many schemes now include the prediction of additional bulk quantities besides just mass. For example, two-moment schemes that predict both mass and number. And I'll mention what I mean by moments in a bit. So you can see a kind of a flow chart of, say, a state-of-the-art two-moment scheme nowadays, which are used in a lot of models, including CESM right now, compared with the original Kessler scheme that's obviously much simpler. So predicted bulk microphysical quantities for each of these categories, like cloud and rain, and then the various ice categories, like cloud ice and snow and so forth, evolve in time and space from advection, microphysical processes, and sedimentation. And that's illustrated by this simple equation here, where the microphysical quantity that's being predicted is this chi, and that's evolves by advection, shown here, sedimentation, which requires some knowledge about the fall speed here, which is this v parameter, and then the microphysical processes. The microphysical process rates in this term out here, like drop evaporation or collision coalescence, depend on the particle size distribution. So we have to say or assume something about the particle size distributions in order to close this set of equations. In bulk schemes, they usually, not always, but usually, some explicit functional form for the drop size distribution is assumed. Most commonly gamma. Some schemes assume log normals, but most often gamma. And I just illustrate that here. D is diameter here, by the way, drop diameter. And then it consists of three parameters: this n naught parameter, which is the intercept, the mu parameter, which is the shape, and the lambda parameter, which is referred to as the slope. So the model predicted variables like the number n, or the mass mixing ratio q, are equal to or proportional to weighted integrals of the DSD. And those weighted integrals are called moments. It's just an illustration of that. N can be related to essentially the 0th moment of the distribution. Mass is proportional to the 3rd moment of the distribution, at least for liquid drops. For ice particles, that's not necessarily true. So these are just weighted integrals, again, weighted by the diameter to some power. So work starting around the same time that Kessler developed his bulk scheme, developed these bin schemes that explicitly model the evolution of the size distribution shape using some kind of size or mass grid, and then one or two quantities which then each of those bins is predicted. So it's a similar equation to the bulk scheme, except now this is chi is like the quantity of that in some ith bin. And usually the number of bins ranges, say, between 35 to maybe 70 or 100. And again, it evolves through advection, sedimentation, and microphysical processes. But it becomes quite challenging to model, at least in a numerical sense, because you have to model how the particles grow across the bins. And there's been work ever since the inception of bin schemes, really, of figuring out how to best do that numerically. Bin schemes are very expensive mainly because they contain many more prognostic variables, and a huge part of that cost is actually just advecting those variables around in the model's dynamical solver, the host model's dynamical solver. So they've mainly confined to research modeling. Again, because of computational costs, they also require relatively fine model grid resolution to resolve cloud dynamics. They're most appropriate for LES or higher resolutions at cloud resolving models. And I mentioned it's numerically challenging to represent the growth across bins. But they have been widely used to test and develop bulk microphysics schemes. I illustrate this from this paper by Krudnoff and Kogan, KK2000, which is a widely used, probably the most widely used scheme for warm microphysics. It's used in CESM as well as a number of other models. And essentially what they did is they ran a bin scheme in LES, large eddy simulations of marine stratocumulus, output the process rates, and then used regression to fit those rates. So the third type of microphysics scheme are these Lagrangian particle-based schemes, which have really kind of come to the fore, like I said, in recent years. Shinichiro Shima really came up with a well-posed way to deal with collision coalescence in these schemes, and since then it's really taken off. That was back in 2009 in his paper. Like I mentioned, the particle populations are represented by a sampling of the so-called superparticles that follow Lagrangian trajectories within the modeled flow. These have some advantages compared with bin microphysics schemes of comparable complexity. In particular, they avoid numerical diffusion that can artificially broaden drop size distributions using bin schemes. That I said it presents some challenging numerics, not just drop growth across bin, but when you combine that with advection in physical space, you can get this spurious broadening of drop size distributions, which in turn can accelerate rain formation relative to Lagrangian schemes. In Lagrangian schemes, it's easy and computationally efficient to add additional attributes of the drops. This would be things like, say, the properties of the solute dissolved within the drops, things like that. So the one advantage of this is like detailed cloud aerosol interactions kind of come with the approach because you can represent the cloud-borne aerosol explicitly. And then I'm not going to go in detail on this point, but it also allows straightforward coupling with subgrid scale fluctuations, which can be very important in driving the particle growth histories. Okay, so now I'll shift gears a little bit and talk specifically about improving warm cloud microphysics schemes. I'll focus on bulk schemes first, and then I'm going to talk about how some details of Lagrangian schemes, how they can be used to improve representation in bulk schemes. So it's again a kind of a motivational slide here. How warm microphysics, and by warm microphysics, I basically mean liquid microphysics, so ice-free conditions. How that's represented in Earth system models has a critical impact on climate simulations. So this illustrates some results from a recent paper by Eidhammer et al., where they ran a PPE, or perturbed parameter ensemble, modifying a whole bunch of different model parameters. They're listed up here. I'm not expecting people to read those at all. And then they compare how these different model outputs, things like top of the atmosphere, rate of fluxes, precipitation, and so forth, how they respond to these changes. These are all kind of normalized changes, and the more kind of brighter a color is, the more sensitive it is to a particular parameter. So the parameters here on the left are from the Zhang-Farling deep convection scheme. The ones in the middle here are aerosol. These are microphysics, and then the one on the right here are for the turbulence or boundary layer parameterization in CESM, which is club. And you can see a whole bunch of these in the microphysics kind of light up here. Those are ones associated with warm microphysics, and particularly the autoconversion and accretion parameters. A few others show up here as being important in the microphysics. This one is the cloud ice to snow autoconversion parameter, which is actually one of the main tuning knobs for long wave radiation and CESM. I would argue it's a completely fake parameter, but we can talk about that later. I'm sticking with liquid microphysics for now. And then this one right here is the cloud ice particle fall speed parameter. So those are also being important. But we'll stick with warm microphysics for now and talk a bit more about some background on that. So current bulk schemes for liquid microphysics still use separate categories for cloud and rain, going back to that original work of Kessler. It's sort of stuck with us. And then this conversion between these categories based on autoconversion and accretion, which is required in order to represent how those drops are growing. In two-moment bulk schemes, which are sort of state-of-the-art schemes used in a lot of models, including CESM and a number of other weather and climate models that predict both mass and number of the clouds and rain, we need to not only include the conversion of mass between these, like in the original Kessler scheme, but also the conversion of number. So a little bit more about how autoconversion and accretion work and what they represent. This is a kind of well-known figure, I would say, from a bin simulation by Barry and Reinhardt in the early 1970s. They started with a simple sort of unimodal cloud drop size distribution, and then it evolved through collision coalescence. And you start to get these embryo raindrops. Time goes back this way, by the way, and then this is drop size here. And you start to get these embryo raindrops forming by collision of cloud droplets. It kind of forms the second mode, and then those raindrops grow by collecting the existing cloud water. And you can see this cloud mode kind of shrinking here. So that initial growth of those embryo raindrops, again, is autoconversion, and then this is the kind of accretion-dominated regime with this growth of existing drops. So kind of the main point here is that we argue that autoconversion is fundamentally ill-posed because it's typically based on some ad hoc threshold mixing ratio. When that gets exceeded, then you have autoconversion. That's how Kessler originally formulated it. Or based on some threshold size to separate the cloud and rain categories. Even separation based on tracking, say, the drops that are formed by collisions from those that have not undergone collisions is still problematic because of the highly nonlinear nature of the problem. It's just to illustrate that for a 20 micron drop to grow to 100 microns, it has to collide with 125 other 20 micron drops. So rain size drops have undergone many, many collisions to get to the size that they are. And again, this matters because, you know, this kind of fundamental ill-posedness of autoconversion because there's large sensitivity of climate simulations to this, particularly in cloud aerosol interactions. So the autoconversion rates are sensitive to this assumed size threshold separating cloud and rain. Adele Eigel discussed this in her paper from a few years ago, and I have another illustration of this in a few slides. So people have used machine learning to try and make this process more robust or at least speed it up and make it more accurate. For example, this paper by Alfonso and Zamora, where they basically improved upon traditional regression approaches like that KK2000 or Krutnoff and Kogan that I already talked about before. But it doesn't really address the underlying ill-posedness of convection, right? You can fit something very well, but if the thing that you're fitting to is ill-posed, that can be problematic still. And I say this may explain, I'm not sure that this is true, but it might be contributing to why Seifert and Rasp, in a paper a few years ago, they developed an ML-based autoconversion scheme, but it gave actually poor results when it was integrated inline. It was very accurate offline, but then inline, it tended to give actually worse results than their original Seifert and Beihang parameterization, which is just a traditional kind of approach for autoconversion. So there is an alternative idea here. Instead of separate cloud and rain categories, why not use a bulk single liquid category? We're not the first ones to suggest this. The first one that I can find in the literature actually goes back to almost 50 years ago now by Terry Clark in 1976, and then some additional work by Clark and Hall in the 80s. They assumed a double log normal DSD or drop size distribution and prognosed 6 of the DSD moments, then use curve fitting and lookup tables for the moment tendencies from coalescence. So machine learning, I guess, I shouldn't say didn't exist back then, I don't really know, but it certainly wasn't used in this kind of thing. But Rodriguez, Gino, and Alfonso basically replaced that curve fitting and lookup table approach with machine learning. Eigel et al. Recently developed another single liquid category. I'll refer to that as SLC, by the way, using double gamma drop size distribution instead of the log normals, and then prognosed between 4 and 6 DSD moments. And the tendencies of those moments from collision coalescence were calculated using a numerical approach called AMP that's basically analogous to a bin scheme. So the way that this works, which I'll describe more in the next slide, but you basically take the double gamma DSD, you discretize it, you solve that like you would a bin microphysics scheme, and then you calculate the change in the moments after that. But you're not keeping track of everything in all the bins, just the bulk moments. So SLC is conceptually better than 2-category schemes, primarily because it avoids this problem of autoconversion. There is no more autoconversion in this approach. There's no separate autoconversion and accretion. These are just considered as one process that affects the moments by collision coalescence. Of course, there are some challenges with this approach. In particular, you need to map between the set of DSD moments and the multimodal DSD parameters, which can be quite difficult. For a single mode gamma distribution, that's analytic, but when you have two, a bimodal, it's no longer analytic. Existing schemes have either relied on lookup tables, weighting factors like the Clark-Hall approach, or an expensive iteration approach, as in the Eigel et al. Paper, and then some more recent paper by Arthur. The other kind of challenge is then how do you actually calculate the tendencies of the prognostic moments? Like I mentioned, this AMP approach from Eigel et al., where they bend it up and do that, but that can be quite computationally expensive as well. So the purpose here is really to develop and test a new computationally efficient SLC scheme and compare it with previous bulk methods in a very kind of systematic way, taking different things apart and really trying to understand why it's different and how it's different from traditional approaches. The basic point is to demonstrate practical viability of this as a bulk approach. So if kind of encapsulate this in a single question, it's can we design an efficient bulk scheme that accurately emulates a detailed scheme with only 4 prognostic variables? So 4 is sort of the number of prognostic variables in traditional 2-category, 2-moment scheme that predicts mass and number of cloud droplets and rain. So I'm not going to spend a lot of time on details of the approach. Happy to talk about that later if people are interested, but I will just highlight a few things. So I talked about these briefly about how this works. So first you have to map between the set of prognostic moments. I show 4 of them here. You can use any number you want, but we've mainly focused on 4, because like I said, that's comparable to the number in traditional 2-category schemes. You have to map that to some size distribution parameters. From that, you can construct the size distribution. You bin it up, like is shown here. You calculate the collision coalescence like you would in a bin scheme. And then from that, you calculate the updated moment values. And then you just do a simple finite difference in time to update those moments. This is expensive. This step in particular is very painful. And we have explored replacing this with a neural network. And I'm going to call that scheme SLC AMP ML. We've also, in addition to that, on top of that, replaced this expensive bin calculation of collision coalescence with just a very simple lookup table. You use a neural net too. We use a lookup table in this case. This is actually very simple and accurate and fast. And I'll call that SLC LTML. And then an alternative is sort of replacing all these steps, 1 through 3, with neural network. So we're getting the tendencies of these moments just directly from the set of moment values here, and then just updating those. So it's sort of going, skipping all these and just going from getting the tendencies and then updating the moments. And I'll call that SLC DML. So we tested this in a box model with various bulk approaches versus a bin microphysics scheme, the Tau scheme, for those of you who are familiar with that, Tel Aviv University. We're using the bin model as a reference. I want to emphasize that there is no real true reference microphysics model, even for warm microphysics, but we're treating it as just a reference point here. Different bin models and Lagrangian models can give very different results. So we have a wide range of initial drop size distribution conditions and 591 simulations. We're integrating forward for 20 minutes, which is roughly the time scale of rain formation, with a 1-second time step. We're testing, like I said, various bulk schemes. This SLC AMP M0346, that just indicates the predicted moments. We're predicting the 0th, 3rd, 4th, and 6th moments. That's sort of the original approach that's expensive. This is the approach where we're replacing that step 1 with the neural net. This is that we're replacing both step 1 and 3 with the neural net and lookup table. This is that direct machine learning approach that we called. We're replacing steps 1 through 3. This SLC fit, we're actually replacing the steps 1 through 3, but instead of using a neural net, we're actually just doing simple power law fit with regression. And then we're comparing that with some traditional 2-category approaches. So the KK2000 scheme that I already mentioned, the Kratnov-Kogan, Seifert and Beheng 2001. And then we're actually developing a KK-like scheme, except that we're using regression on the output from the bin model for these simulations. So it's a little more of a fair comparison, because Kratnov and Kogan use a different bin model, for example, to do their fitting. And then finally, we're testing with this traditional two-category scheme, but it's actually using AMP to solve the collision coalescence rate. So in other words, we're taking the cloud and rain modes like a traditional scheme, we're bending that up, we're solving the rates, and then we're calculating how the cloud and rain change from that. This is similar to Andrew Gettleman's ML-based approach that some of you may be familiar with. This does require a size threshold to separate cloud and rain. I'll show some results of that. But you can basically think of this two-cat AMP as being the best that a traditional two-category scheme will do, because it's using an explicit calculation of the collision coalescence rates. Okay, I'll step through some results here. So this shows different tests, again, relative to the bin scheme that's serving as the reference. The top shows mean absolute error for the 0th moment. So this is drop number in this upper left here, and it's normalized errors here. And then on the right here is the 6th moment of the drop size distribution, which is weighted heavily towards large drops. So you can sort of think of this as being a signature for sort of the development of rain. So we're showing errors in that, and this is in log space, actually. This varies by many orders of magnitude during the course of the simulations. And then on the bottom here are showing the error quartiles. So one thing that jumps out here is the original kind of SLC approach in black. This SLC AMP ML, we're replacing step 1 with ML, and then this SLC LT ML all give roughly comparable results here. That SLC DML, which is the sort of direct machine learning replacing steps 1 to 3, does have some increase in error here, roughly a factor of 2, I would say. But doing the direct fitting, so this is just regression of power law, produces much larger error in that. So it's showing that that's just insufficient as a way to represent the collision coalescence tendencies of the moments. So we're comparing this now with the two-cat AMP. Again, you can think of this as being like the best that the traditional two-category scheme can do. And like I said, this requires a threshold drop diameter to separate cloud and rain. And we tested different values. That's the different colored lines here. Everything are drop diameter thresholds of 50 to 100 microns. And that's generally the range that's used in existing parameterizations. And the point here is that all the errors, regardless of what that threshold is set to, are larger than the black line here, if you look at the errors, especially in the higher order moments here. And there is a lot of sensitivity to that particular threshold that's being set to in all these, especially in the sort of earlier spin up time. You get a lot of sensitivity of the rain formation to that threshold size that, again, is more or less an ad hoc parameter. There's not really a physical constraint on that. Okay, so this finally shows some results of SLC versus the traditional two-category schemes. And these schemes produce much larger error. Even the two-cat fit here, where we're actually fitting to the bin model simulation that's being used for evaluation, it still produces, it's less than KK, at least in the case of drop number, but much larger, about 5 to 10 times larger compared with the SLC. So one of the main motivators for this was to ask the question, can we actually make SLC into a viable scheme? Because the existing approaches for it are very expensive. So this just shows timing tests for this. These are averaged over 5 realizations for all those 591 simulations on Perlmutter. And this just gives the wall clock time for that. And you can see here the original approach, and I coded this up differently from how Adele and Arthur did. So my method is probably especially clunky because it basically takes a day to run those simulations. Replacing that step with the neural net obviously reduces the, whatever that is, a factor of 10,000 or something in timing. Reducing that with a lookup table then begins to bring it down closer to the cost of the traditional two-category schemes. They're very simple. I mean, KK2000 is just a power law for the auto-conversion accretion rates. So it's very, very fast. Okay, so to briefly summarize these results and to take a quick breath, using a using a single liquid category, so SLC, instead of the traditional approach of separate cloud and rain, combined with machine learning, gives accurate results for reasonable costs in a box model. So we're pretty hopeful that indeed this is a viable approach. The approach can be really extended to other processes besides collision-coalescence. All those tests I showed before included only collision-coalescence because we started with a drop size distribution, and that's, let it evolve from that process. The scheme can be further refined using advances in detailed cloud models, in particular Lagrangian particle-based schemes and high-resolution large eddy simulations. I'll give one example of that. We believe that in a lot of, in certain cases, turbulent enhanced collision coalescence can be quite important. So that can be kind of included in this framework, just neglected in the box model simulations that I showed. They only use the gravitational collection kernel. So with advances in computing power, high-resolution LES, or DNS, with Lagrangian microphysics can provide detailed data sets for training a wide variety of ML applications in cloud physics, turbulence, and cloud parameterization development. So I'm going to take a sip of tea, and I'll give some examples of these kind of high-resolution simulations. Okay, so I'm going to show LES with Lagrangian physics, and we're calling this approach a virtual cloud physics laboratory because we're essentially modeling a lot of these processes kind of at their native scale. We're modeling most of these scales of motion that are driving the clouds. Really getting into the process level kind of details. We're using here Cloud Model 1, or CM1, developed by George Bryan, with Shinichiro Shima's super droplet method, and that was implemented into CM1 by Kamal Khan Chandrakar, and he's continuing to do a lot of development on that, really kind of leading that effort. In the example I'm going to show here, we're simulating a precipitating cumulus congestus cloud with 7.5 meter grid spacing, and the domain, I don't say the size here, but it's a domain that's roughly 15 by 15 by kilometers in the horizontal and 10 kilometers tall. We're modeling the full cycle cloud growth and microphysical processes, including droplet activation, condensation, evaporation, and collision coalescence. This is liquid only, so it's a warm cloud. And I mentioned the turbulent enhancement of collision coalescence can be quite important. That is included here. We're taking a case study from the Camp 2X field campaign. For those of you who might be familiar with that, it took place about 5 years ago, I guess, in the Western Pacific near the Philippines. These runs are expensive. So 3 of them cost about 50 million core hours on derecho. So we were basically beta testers on derecho when they were setting up the machine, and they awarded us this large allocation to basically, kind of put it through the ringer. And a lot of data comes out of this, about 1.5 petabytes. And I want to emphasize and thank Kamal for really doing the heavy lifting of performing these runs. So here's just some visualizations of it. These are at different times. These are visualizations by Matt Remy at NCAR using Blender. And, if you were going to squint, those look pretty realistic, just very realistic clouds. This one in the bottom actually shows on the left panel here a picture from Paul Lawson of the cloud from the case from a cockpit of an airplane. And then this one right here just shows a zoomed in section right here of this one. And you really see the structure of entrainment and mixing in these clouds along that edge in a kind of I would say, visually pretty stunning way. And as I'll show in a few slides, like that process of mixing and entrainment and what's happening along the cloud edge is really critical to how the cloud microphysics evolves. And I think I have enough time to show the video of this. There we go. You can see the kind of bubbly nature of convection. If you look at a time lapse of a cumulus cloud, it looks very much like us. Then it develops and begins to precipitate. And then the camera is going to zoom in here. Look at some of the details. The interesting thing here is you can see, Marcus and I were talking about this last night, you can see the really sharp edge in the interface right where it's coming up. That's like that cauliflower-like structure. And then where the cloud is beginning to precipitate and detrain a lot and mix, you see it's much more diffuse and fuzzy. And you see that in real clouds. Next time you have some good cumulus clouds here, go and look at that. So, looking at pretty pictures is nice, but the big advantage of these is we can dissect those clouds and actually look at the details of the fields. So here's an illustration of the dynamical fields from that run. This is just showing vertical velocity and the color contours. The black line here is the cloud boundary. And there's a really cool structure that comes out of this in that the cloud consists of these cloud scale thermals. So they're about as wide as the cloud itself, and they rise up and decay. And then another one underneath rises up and decay. And we've spent quite a bit of time in the last few years really kind of looking into that structure that we call the thermal chain and basically understanding why it occurs and its behavior and so forth. But you see that in this structure here, or you see in the simulation here. This is just a vertical cross section through the cloud center. And these are 2-minute time increments here. And you see this pulse, a relatively high vertical velocity that corresponds with the center of this circulation. So it has a toroid-like circulation that goes like this, and the whole thing rises up, which you can illustrate here. Sort of the center of that is in this plus sign here. And it rises at a rate about 4 meters a second, which is about half or 40% of the maximum vertical velocity. And there's a reason why that ratio happens at this. I won't get into that. But you clearly see that behavior where this thing rises up. By here, it's sort of making it up to the cloud top, and then it just falls apart. And then you actually see a new one underneath that that's doing the same thing. And if this run kept going, you'd see another one, until eventually the whole cloud might decay. But that's really critical for driving the microphysics. So I mentioned you get this toroid-like circulation around here. That's critical for driving entrainment. And this isn't just this cloud. This is believed to be true for cumulus clouds generally. So I mentioned that you get a circulation that looks like this and this. I'm assuming you can see that on there, good. And because you get inflowing air in the circulation like here, it drives dry environmental air into the cloud. You can even see that in the shape of the cloud boundary. It goes in right here. That's the entrainment process happening. You get these pulses of dry air that come in, and as I'll show in the next slide, that's really critical for how the drop size distributions evolve. So this shows vertical cross sections. This is actually a different simulation than the last one. This is a non-precipitating one, just to keep things a little simpler, but it still has that same kind of dynamical structure of these rising thermals. So the top here shows vertical cross sections of the mean drop radius. This shows radius standard deviation. You can just think of that as size distribution width. This shows the mass mixing ratio, and this shows the number of drops, number mixing ratio. On the right here are just a zoomed in view in the black box here in all these. So you can really see this structure here. Here there's this rising thermal with a structure like this. And again, it's driving entrainment in right here, especially on this up shear side of the storm. There is shear in the simulation, which you might have guessed as to why the whole cloud is leaning over. But you see small mean drop radius here. And most remarkably, I think you see very sharp gradients in the size distribution properties right here. It's almost step function like here, where you have air that's relatively undilute right here with narrow drop size distributions. And then you have air that's a combination of cloud air and environmental air owing to entrainment and mixing in here with very wide drop size distributions. And in part, that's because you get the activation of new drops on entrained aerosol. So in a lot of cases, there's even bimodal spectra as a result of that. Interestingly, because you get drop activation on aerosols that are being entrained in, the droplet number is relatively constant in here. Like you don't see those really sharp gradients like you do here. Okay, so this wasn't based on an observed case. So this is just a very simple comparison of drop size distributions that come from these simulations with ones that were measured by aircraft at 5 different heights in the cloud. So the red is the observed. Black is cases with the simulation with collision coalescence turned on, and blue is the simulation without collision coalescence. So obviously, the presence of the tail here, or really any drops larger than about 50 microns, is due to collision coalescence. They can only get to about 50 microns growing by condensation alone. But you can see a pretty good correspondence here with the aircraft observed drop size distributions. I don't show this here explicitly, but especially down in here, the tail of this distribution is basically caused by turbulent enhanced collision coalescence. Without that, this distribution would just drop off like this. It would be very similar to the no collision coalescence case, lower in the cloud here especially. And there's a paper by Kamal recently came out in PNAS that really illustrates that for different set of simulations, but the same case.
Have you included also the components of the aerosol?
I didn't quite, the components of the aerosol?
Yes, because when I studied this, I simulated, I used the CO2 laser.
Yeah, so what we did.
I built a fog chamber and I measured the absorption coefficient.
Okay, yeah, what we did
And
in
I
this
detected when it was the proper size, the fog was created, and if it was another particle, an element, it was able to be detected. I did this in 1975.
Okay, yeah, what we did in this simulation for the aerosol conditions is it's based on observations that were taken during the Camp QX field campaign. And it's initially uniform horizontally, and we scaled it vertically with height based on the observations. With the Lagrangian microphysics scheme, what you do is you sort of initialize it with aerosol particles. Those aerosol particles get transported around or whatever, and then they can activate in the cloud. So I'm just showing the cloud part of it here, but if you go and look in here, there are aerosol all around here too that are being explicitly modeled with this approach. I'm just not showing here. By drop mean radius, I mean specifically the cloud droplet part. So these are droplets that are above their polar activation size. Okay, we can extend this approach to also simulate laboratory cloud chambers. So this kind of virtual laboratory approach. This is basically can fill in measurement gaps. Even in a laboratory, some things are very difficult to measure, like supersaturation, which is maybe surprising. We were talking about that yesterday about why that is. I'm not a measurement person, so I'm not exactly sure, but I've been told that you can't get highly accurate supersaturation, even in a lab setting. And it can serve as a benchmark for testing lower resolution models. So we're looking here at direct numerical simulation of Michigan Tech pi chamber. And just again to highlight, so DNS or direct numerical simulation is resolving all scales of turbulence down the Kolmogorov scale. So in this case, we're using a grid spacing down to about a millimeter with that, or a couple millimeters. And then it's even finer near the boundaries. So we're simulating the Michigan Tech cloud chamber, which works as a convection cloud chamber. It's got heating down here, cooling above at the upper boundary, which drives convection in the chamber. And we basically simulate that with realistic boundary conditions and at the scale of the chamber itself. So this is another quite intensive simulation in terms of its cost. We did a few different simulations with different aerosol injection rates, and you can see the drop size distributions that follow from this. Again, the chamber is too small to really grow large drops here. There's essentially no collision coalescence or very little, so the maximum drop size here is about 30 microns. We can take snapshots through this. These are vertical and horizontal cross sections just to get a sense of what different fields are like. So temperature, vertical velocity, drop number, and again, supersaturation, which is of key importance because it's controls drop condensation evaporation rates. And you can see this really detailed structure in here. You see the large scale circulation associated with the turnover of the Rayleigh-Bernard chamber. Associated with this, you can see in the vertical velocity field, and sort of see the imprint of that in the supersaturation as well. Okay, so I'm almost done. Just a few wrap-up things here. So far, this talk is focused on development of bulk warm microphysics, mainly at LES scales, like I said. This is why I said toward Earth system models. I didn't say just Earth system models. The coarse grid spacing and long time steps of traditional global models presents major challenges. In particular, so this requires coupling of microphysics with macrophysics. I mentioned that early on, like in slide 3. And I should mention also requires coupling with convection schemes in traditional global models that are not convection permitting, which also presents challenges. Long time steps can lead to large truncation errors, and there are not very many people working on that. Sean Santos at PNNL is one of them, showing that can be really important and something that's not typically considered in a lot of microphysics scheme developments. I did look at this a bit, and this is the last slide that I have with science in it. So we looked at these box model tests again. These are the same 591 simulations, but using a 5-minute time step instead of the 1-second time step. And I'm showing these results again relative to the bin results at 1 second. Again, this shows the error and drop number, M0, and this shows the error in the higher order moment. The solid lines here are the 1-second results. The cross lines, the cross symbols are the 5-minute results. And I'm also including Andrew's Gettleman's 2021 machine learn type approach in here as well, which does reduce error quite a bit relative to KK. But again, it's sort of limited by using the traditional 2 categories, separate cloud and rain. We do see errors with the SLC approach that increase quite a bit relative to using 1-second time steps as expected. Again, that's just time truncation errors, but the errors are still relatively small, even in that case. So we have hope that using it in a longer time step might be sensible. All right, this is the last slide, just a few summary points. Warm cloud microphysics is of critical importance in Earth system models. I don't think I have to do too much arm twisting here to convince you of that. The SLC approach, that single liquid category combined with machine learning, is a promising alternative. Offline box model test showed substantially reduced error. Of course, the next thing is to really test this in a 3D dynamical model, and that's one of the reasons I'm out here. We're putting it into CM1 and want to test it for some LES cases. Further advances in warm microphysics, particularly using Lagrangian super droplet schemes, which have some advantages relative to bin schemes, and high-resolution dynamical models combined with detailed observations hold significant promise in further improving schemes, including using data-driven approaches. And again, this work is really just a first step toward improving this in our system models. And again, the major challenge is, of course, grid spacing, long time steps, and the macrophysics, microphysics problem, this parameterization squared. And with that, I'm happy to take questions. I noticed on the end here, this is definitely not a warm cloud. There's a lot of ice in it.
If anyone in the room has questions?
Sure, I can start. Thanks, Hugh. Really interesting work. I'm wondering, in that last slide you showed, did you do any, for the time steps, did you do any retraining, or you just propagate the tendencies from the 1 second and to 5 minutes?
I should clarify. So I'm actually using the direct kind of numerical solver that was used to develop the training in Andrew's method. So this actually is not using the machine learned approach with that method. It's what they call the tau solver in that. So there was no retrain or anything. It's just using tau to directly solve the rates, but at that 5-minute step.
So tau is taking a 5-minute time step.
Yes.
Okay.
No, tau is taken at a 1 second time step, but it's integrated forward in time for 5 minutes. And then that's used to get the rates and applied to the bulk variables. So the cloud and rain number and mass at the 5-minute time step, and that's integrated. So it's kind of like a multi-step sort of approach where tau is integrated at a short time step, but then the rates are applied to the bulk quantities at the 5-minute step. Basically, you can think of it as like an averaging of what's happening over the 5 minutes with tau. Yep.
And your method, what for the SLC method, do you?
Oh yeah, that's for the G2021. For the SLC, we are essentially doing the same thing, except we're operating on just the single category instead of separate cloud and rain. So it basically boils down to how the rates are derived from that. Like, are they derived based on this threshold size and kind of separating like that? Or is it just derived by integrating the full drop size distribution moment tendencies over those 5 minutes? Yep. So it kind of represents a clean test in a lot of ways of the different methods, because they're using the same solver, essentially. They're using tau as the solver to do both. Of course, not in these methods down here, in KK2000 or SP2001. So they're doing their own thing.
If there's anyone online who wants to ask a question, you can feel free. If not, I have a little question. So sort of like looking broadly at the problem of like bulk microphysics, where do you see the largest contribution of errors sort of across scales If you're thinking about like global models, if you're thinking of like these kind of convection allowing models, and then LES models.
Okay, yeah, that's a very
Small question.
might need some beer for that one. That, I mean, I think it's hard to give one answer across scales because the uncertainties that you get in DNS are going to be very different from the uncertainties you get in LES or cloud, resolving models or global models. So it really kind of depends on the scale. It depends on the regime too. Like here I focus on warm microphysics, but like I mentioned, and of course, as you know, ice microphysics presents a lot of unique challenges. Just we know that there's a wide variety of ice particle shapes, of course, and different growth mechanisms. So I think there is kind of a crossing point, though, when you go from LES to everything that's larger scale than LES, then you're presented with problems of the cloud dynamics and the coupling with that, right? In LES, we have good, well-posed turbulence closures based on scalings so that we aren't resolving like every scale of turbulence because we're not DNS, but you can still like parameterize that, I would say, in a sensible way. But when you get away from those scales, all of a sudden you're not really resolving even the driving scales of most in like convection. Even a 250 meter or 500 meter grid spacing model will not resolve convection, especially shallow convection, right? It's under resolved and that presents its own kind of challenges. And then I think as you go up and scale from there, the problems just kind of compound. And this is my own sort of thinking on this. I guess people could argue if they wanted, but at a certain point, I think the microphysics uncertainties might almost get just lost in the macrophysics part and the coupling between the two. It goes back to that parameterization squared problem. And you can maybe argue philosophically, like if you have huge uncertainties in your macrophysics, like your cloud fraction, subgrid scale distributions, does it even make sense to try and put in a detailed microphysics scheme when everything that's driving it is uncertain anyway? I would argue probably not. So yeah, I think it's just like, to just summarize that very briefly, as you go up in scale, you're presented with just kind of compounding problems. Even at DNS, though, still a lot of uncertainties just in, we don't know how ice particles grow that much. I mean, there's people working on it like Jerry Harrington, but there's a lot of uncertainties with that.
Don't you think there are some thresholds?
Sorry, could you repeat your question again?
I was thinking maybe there are some thresholds. So if you reach those, then the other process will happen.
I guess thresholds in like particle types, you mean, or I'm not quite clear.
Type, size, structure.
I think to some extent that's true because, I mean, the classic example of, or
because when you go
to
the quantum mechanics, combining with the spectroscopy.
Sorry, I didn't quite understand that. Okay. Well, okay. So the simple example of, if the cloud doesn't have ice, you don't have to worry about ice microphysics. But I guess since we're thinking of global models here, you really have to consider all these different regimes and how to model them. There are maybe some arguments too that if process rates can happen very fast, like rhyming, for example, if rhyming is a very fast process, maybe you don't have to worry about these partially rhymed states. And you can think, oh, a particle, you can treat it either like sort of a puffy snowflake that's not rhymed or a droplet. But it turns out that there's just too much variability in different cloud regimes. You do have, in that particular example, there is partial rhyming where particles will collect a bit of rhyme, but they're not yet fully rhymed like droplet or hail. And that can be really important in some cases. So I think, yeah, we try and simplify stuff with some of this thresholding and whatnot, but I think it's hard to really make it general then to apply to all conditions.
Okay, we're running a little bit late on time, so if we could just thank Hugh again, and he's sticking around for lunch, so if you want to ask questions, you can hunt him down there. Thank you.